Now we've excuse me, derived the equations of motion from a simple trapezoid on a V versus T graph, where we specified V naught, VF, and delta T in terms of the graph. We look at the area under the curve and find that that's equal to average velocity times delta T, average velocity being the average of initial and final velocities, because the graph is linear, straight line. The V bar here is noted right at the midpoint of the straight line segment. The slope and the area under the curve give us the first two equations that I've written up there, and elimination of delta T between these two equations. In other words, solving, let's say, the first equation, which is the easier for delta T, and then plugging the result in here gives us this equation. And then just plugging VF equals V naught plus A delta T into the second equation, replacing VF by this expression and doing a little arithmetic, well, a little algebra, a little simple algebra, gives us this equation. Now we can derive the equations from calculus as well, just knowing that acceleration is the rate of change of velocity and velocity is the rate of change of position. With respect to time in both cases, it probably with respect to T in both cases, because that's important, and that's left out from a lot of the language you see in the text. So they just talk about the rate of change of velocity or the rate of change of position. And that's okay, except that it gets a little confusing later when you have velocity as a function of position. So it's no longer the rate of change of velocity with respect to time, it's the rate of change of velocity with respect to position. And it's easy to get a little bit confused there if we're not really careful about the language. Okay, anyhow, assuming acceleration to be constant, which relates to the linearity of the V versus T graph, same thing. Acceleration is constant because acceleration is the curve, the slope of that graph. If the slope is constant, then the graph is linear. If the graph is linear, the slope is constant. So that the acceleration is constant. Okay. The definition that comes, or the equation that comes from acceleration being the rate of change of velocity with respect to time, is acceleration is dv dt. Now, this acceleration would be a function of time. But if acceleration is uniform and constant, then it's a constant function of time, which makes it easy to calculate what the velocity would be. Because, of course, if the acceleration is the time derivative of velocity, then by the first fundamental theorem of calculus, velocity is an integral with respect to time. That's your dt of the acceleration. You need to understand that about calculus, and people come out of calculus, one especially, with just the ability to manipulate symbols and change variables and use substitutions and integration by parts, and then do some sequence and series and a bunch of other stuff without ever really understanding what this notation tells them. So think about it. Anyhow, it's real easy to integrate A dt when we know that A is constant. We just get AT plus an integration constant. So V is AT plus C. Now this would be velocity as a function of time. Okay, so we could write V of T here if we wished. V of 0 is C constant, or integration constant. So instead of C, let's use V naught, which stands for V of 0. C is equal to V of 0, V naught is equal to V of 0, then C becomes V of 0. And here's our equation. And notice that this maps very nicely onto equation 2 that we got from the trapezoid. Okay. Now, we also know the velocity is the rate of change of position with respect to time. So V is dx dt if we use x for position. And as a result, x is antiderivative of v with respect to t, or an integral of v with respect to t. So we integrate v with respect to t, but v is at plus v naught. Integrating that with respect to t, well, it's almost a trivial integration. Make sure you can do that. And you get 1/2 at squared plus v naught t plus c. Well, as we did letting v of 0 be v naught, we're going to let x of 0 be x naught. So instead of c, we're going to use x naught. And I put it at the beginning rather than at the end, but c is just x naught. And there's our x of t function, which looks a whole lot like this. One of the equations we derived from the trapezoid. So there's a difference in the calculus derivation and the trapezoid derivation, no difference in the final result, which can be expressed in a number of ways. For example, in this case, I use delta x. In this case, I include x naught. But x of t minus x naught would be your delta x. And that's equal to v naught delta t plus 1/2 a delta t squared, where we're using delta t over here and t here. These equations apply to some interval of motion. Okay, these equations can be thought of as giving you everything as a function of time. Okay, so we've gotten equations 2 and equation 3. Okay, and I mentioned that I have a grandson who came through these courses a few years ago. Successful career so far as an engineer. He didn't even want to think about the trapezoid. Okay. The calculus was so obvious and easy to him that he just used the calculus. Okay. You should be able to do both, but if you can only do one, it should probably be the calculus. It's a calculus-based course and so forth. And I actually didn't complete this thing to tell you where fourth equation comes from, but we eliminate delta t or t from these equations, we get fourth equation, which is practically the same as this, although here we can think of v as a function of t. Here it's just a final velocity in some interval, but it's, you know, one is equivalent to the other. Okay, so this would be our fourth equation. And why did I call this equation 2? This was equation 1. Okay. So the one equation that we got that's pretty much the same between the two ways of deriving is the second equation. First equation comes from the second and third equation from the calculus derivation if we eliminate a. It comes pretty directly from the trapezoid if we use trapezoid. Okay, well, there it is. You should be able to derive it either way, both ways. And if you can, gives you more insight into what the variables mean and so forth. Now, the final thing I think I said, and it wasn't on the original video, you got 5 quantities. Here, on this side, we got V naught, VF, delta X, delta T, and A. Here, we got V naught, V, X, T, and A, and we got that X naught in there. But I kind of eliminate it when I do this. In any case, it's the same 5 variables, basically. There are 5 variables, whichever equation you want to use. Okay, 5 quantities that you need to determine. If you look at the equations, they have the property that there are first of all, 4 equations. Each equation involves 4 of the 5 quantities. Okay? In this equation, 4 of the 5 of these. In this equation, 4 of the 5 of these. You should verify that for yourself. Doesn't take long. Just look and make sure that every equation contains 4 quantities and that they're these quantities. Now, the big thing is, if I know any 3 of these quantities, I can find an equation that has those 3. And since each equation has only 4 of them, I can solve for the 4th one. And then once I've done that, I know 4 quantities, and it's easy to find an equation to solve for the one you still need. So that's the beauty of this system of equations, either in this form or in this form. So learn to identify what your variables are. And that's something that we commented earlier, people calculate things without identifying them. You see a displacement and a time, and you divide the one by the other, which is appropriate, but you don't identify what it is. So without having that thing identified there in your paper, it's harder to think about what to do next. And you sit there scratching your head because you haven't identified what you're doing and you haven't related everything back to rate of change. Now, I emphasize there are several things that need to come together to have a deep understanding of this topic, okay? Just the uniform acceleration, okay? You have to have an intuition about what it means, and you do pretty much have an intuition about what velocity means. Acceleration, less so, but I think you're developing that. You have to know how to formulate it. You have to know how it proceeds from the definitions. And in both cases, we've proceeded from definition of rate of change, okay? That's a fundamental definition. It's a fundamental definition in calculus. And then you have experience in problem solving. So when you solve the problem, pick the easiest way. Pick the most straightforward way. And I mean the most easiest valid way. The easiest way is to ask an AI to solve it for you and copy it down and pretend you did it. You know better than that. Okay? Ask AI to explain a concept to you. It'll usually do a pretty good job. Ask AI to give you examples of uniform acceleration problems. It'll probably do a pretty good job. Solutions didn't used to be too good at that, but I think it's gotten better. So I wouldn't trust it completely for the solution of a given problem. It makes up numbers. It still probably has a tendency to do that. It was awful when it first came out. But I think they got that reconciled pretty quickly. I haven't tried to use it for that because I don't really have a need. But I have time. I want to do a lot more with in prompting the AI and so forth, and actually seeing what it's good for at this point. But I know from what other people say that it's pretty good. And from what I saw even 2 years ago, it was pretty good with concepts. I could ask it questions about really advanced physics topics, general relativity, quantum mechanics, and I couldn't identify any flaws in the answers it gave me. Trivial stuff like give me 10 linear equations and tell me what the solutions are. It'll give me perfectly 10 good linear equations and give it a format. But the solutions were totally unrelated to the equations. Anyhow, that's AI. My point is when you're solving a problem, solve it. If you got to find an equation, make sure you got the right equation. Make sure you know what the definitions are of the different quantities and make sure that you're saying what you think you're saying. Don't just pull out some formulas that seem to have the right letters in it. Do the units, check the units, because that's a dead giveaway. If the units don't work out, you did something wrong. Okay? Pulled out the wrong equation or something went haywire. think about your intuition. Think about situations where you're seeing. We try to build those situations in lab and analyze them to reinforce what's going on in class. Pull all different ways you can, at least on each problem. Try to see it in two different ways. Try to, if you use a formula to do it, okay, then think back. What's this mean? Why would that make sense? What are the definitions? Something besides just getting the right answer. You will save time in the long run and learn much better. Very beneficial to you as you go through your curriculum. Okay, well, I think that's pretty much the content of everything I originally said. So there we have it. And good luck on the homework and the lab assignments. And see you on Monday.